September 2019. Business news. Somewhere between the reports on trade wars and exchange rates, a short announcement. The Chinese mining company Somain Resource Group is acquiring the Canadian division of the American corporation CAT. The deal was quiet, without press conferences or front-page headlines. No one really noticed, and in vain, because this division controlled a deposit near Bernick Lake in the Canadian province of Manitoba. And Bernick Lake contains 70% of the world's reserves of a single metal. A metal without which no satellite navigation system on the planet works, without which they don't drill ultra-deep oil wells, without which they don't build quantum computers, without which your phone doesn't know what time it is. After the deal, control over 70% of the world's reserves of this metal passed to a company from a country that is simultaneously building its own satellite navigation system, developing quantum technologies, and expanding its nuclear energy industry. You think it was a coincidence? What kind of metal is this? Most people don't know it, even though they use it every day. Even though it's in your pocket right now. Even though it's the one that determines how accurately your GPS knows where you are. Its name is Cesium element number 55. And this is it. Friends, this is the Fool's Gold channel. Here we are breaking down the periodic table, element by element, story by story. Sometimes gripping, sometimes creepy, but always honest. By the way, I periodically see questions in the comments about the reliability of the information in our videos. Well, I spend a lot of time on this aspect, constantly double-checking the facts. But I digress. Today's hero of our video is Cesium. And after this episode, you'll likely be Googling what kind of watch you have on your phone. I've warned you. But before we get to geopolitics, oil wells, and quantum computers, we need to understand something fundamental. A question that sounds trivial at first glance. What is 1 per second? Oh, seriously, most people would say 1/6 of a minute. Okay, and a minute is 1/6 of an hour. An hour of one day. A day is the Earth's rotation around its axis. Woo! Overall, it's all pretty logical. But here's a detail that they somehow forget to mention in school. The Earth's rotation is uneven. It slows down due to the movement of water masses in the oceans, due to melting glaciers, even due to earthquakes. By the way, an interesting fact. After the major earthquake in Japan in 2011, a day became 1.8 microseconds shorter because the mass inside the planet shifted. The Earth's rotation speed is not constant. It's variable. If a second is a derivative of the Earth's rotation, and the rotation is unstable, then the second is unstable. And if a second is unstable, everything based on it also fluctuates. Physics, navigation, communications, financial transactions. By the mid-20th century, this ceased to be a theoretical discussion and became a practical problem. Military and strategic. Synchronizing radar stations, guiding missiles, coordinating submarines, all required timing that could be trusted to the nearest hundredth of a second. And the Earth, it turned out, wasn't worthy of such trust. And then Cesium entered the picture. It's only fair to start by explaining what kind of creature it is. Cesium is an alkali metal, the same class as sodium and potassium, only taken to the extreme. Sodium reacts violently with water, beautiful sparks, hissing, a flame. Cesium reacts catastrophically with water, an instant flash, an explosion, a scattering of hot droplets. Sodium in water, fireworks. Cesium in water is a completely different category of events. It's soft as butter. You can cut it with a knife, it melts right in your hands. Its melting point is 28.4 degrees Celsius. That's below body temperature. Place it in your palm, and it will flow, then catch fire, then explode. It's gold and silver in color, with a slight yellow tint, almost like gold, It's beautiful when viewed through the glass of the ampoule, in which it's stored under argon or in a vacuum, because it oxidizes instantly in air, but in air, it lasts only seconds. Such is the irony. The element that measures seconds doesn't survive them in open air. Atomic number 55. Atomic mass approximately 132.9 under. Atomic mass units. It's in group 1, period 6 of the periodic table. Above it is rubidium, below it is francium. Francium is the most unstable alkali metal, almost non-existent in nature. We'll talk about it in a separate issue very soon. Cesium, on the other hand, is the heaviest stable element in its group. It's the boundary between a stable and an unstable world. It occurs in nature as a single stable isotope, Cesium-133. Remember this number. It will return with a bang. Cesium was discovered in 1860, and the method of discovery itself is more than just a historical fact. It was a turning point in chemistry. Two German scientists, Robert Bunsen and Gustav Kirchhoff, were working in Heidelberg. The name Bunsen may sound familiar, and rightly so. The Bunsen burner. That same gas burner that stands in every school and university chemistry lab in the world. It was his invention. But the burner, as it turns out, was far from the most important thing he did in his life. In 1859, Bunsen and Kirchhoff together developed a method of spectral analysis. The idea is simple, almost ingenious. Every element, when heated to glow, emits light of strictly defined wavelengths. Each element has its own unique set of lines in the spectrum. Spectral passport. Sodium, bright yellow, potassium, violet, lithium, red. No coincidences. In 1860, Bunsen began systematically analyzing mineral waters from German springs. He evaporated a huge amount of water. According to some sources, it was tens of tons. Tens of tons of water evaporated for the sake of a pinch of sediment. After evaporation, spectral analysis, and suddenly 2 new lines appeared in the spectrum. Dark blue, almost light blue. No known element produced such lines. Bunsen realized this was something new. He named the element cesium, from the Latin word cesius, meaning sky blue. He named it cesium after the color of the spectral lines, not by the appearance of the metal, but by the color of the light the element emits when it burns. A beautiful name for a beautiful discovery. This was the first ever discovery of a chemical element using spectroscopy. A method that had previously existed only in theory received brilliant practical confirmation. A few months later, rubidium was discovered using the same method. Then, thallium, indium, and helium. So, in just a few decades, spectroscopy reshaped the periodic table and gave humanity a way to determine the composition of stars millions of light years away. Light from a distant star passes through a prism, disperses into a rainbow, and in this rainbow, dark lines and dips are visible. Each element leaves its own unique set of such lines, like fingerprints. Hydrogen has its own pattern, helium has its own, iron has its own. You don't need to fly to the star. You don't need to take a sample. Just capture its light and read it. Bunsen and Kirchhoff, without realizing it, gave astronomers the key to the entire universe. And it all started with them simply wanting to understand why a flame with a residue burns blue. Bunsen couldn't know this. He simply looked at the blue light and wondered what it was. But let's return to the question of the second, because this is where cesium transforms from a laboratory curiosity into the foundation of the global infrastructure. In 1945, the American physicist Isidore Rabi put forward the idea, what if we use atomic vibrations as a standard of time? Atoms do not get tired, do not slow down because of the moon, are not affected by the weather. Atomic transitions are reproduced with absolute accuracy at any point in the universe. Rabi proposed, and then they began to think about which atom. And Cesium-133 turned out to be an ideal candidate. The Cesium-133 atom, when it transitions between two specific energy levels of its outer electron, emits microwave radiation with a frequency of 9.192 600 oscillations per second. This is not a rounded or approximate number. This is an exact property of the atom itself. Physics. In 1967, at the 13th General Conference on Weights and Measures in Paris, the second was officially redefined at the international level. 1 second is exactly 9.192.126. periods of radiation of the cesium-133 atom. Not the rotation of the Earth. Not pendulum atom. The Earth is no longer a standard of time. Cesium is. The first cesium-based atomic clock was built by physicist Louis Estienne and his colleague Jack Parry in 1955 at the UK National Physical Laboratory. The setup took up an entire room, hummed, and required constant maintenance. It looked nothing like a clock, an error of 1 second every 300 years. Amazing accuracy. Really? Back then it seemed like science fiction. Today, modern atomic clocks are off by 1 second every 300 million years. Dinosaurs became extinct 66 million years ago. During that time, an atomic clock would be off by less than a quarter of a second. And you benefit from that accuracy every day. The global positioning system only works because every satellite has an atomic clock. Take away cesium, navigation would stop working in a few minutes. Every bank transfer is time-stamped by an atomic clock. Every cell phone base station synchronizes to it. You know, when I realized that, I actually stopped and thought, take away an element from the periodic table, and that's it. Navigators are going blind, banks can't confirm transfers, cell phone service is falling apart, the internet is starting to glitch. Not a war, not an asteroid, not a virus. It's just that a soft metal that most people haven't even heard of disappears, and the modern world comes to a standstill. There's something humiliating about this, to be honest. Our entire civilization hangs on an element that melts in our hands. That was a moment of philosophizing. Let's move on. So, for cesium to become a foundation, it first had to be mined. And here we return to the beginning. The only industrially significant mineral of cesium is pulsite, silica, cesium, and aluminum. The largest deposit is Lake Burnett, Canada. 70% of the world's reserves. The second is in Namibia. There are reserves in Zimbabwe, Kazakhstan, and China, but Canada dominates by a huge margin. The concentration of cesium in the Earth's crust is about 2 to 3 milligrams of rock, about as much as the waste and more than molybdenum. Significantly more than gold, but the problem is that cesium is almost never concentrated in its pure form. It's dispersed in rocks and only rarely forms its own mineral, pollucite. Annual global production is several dozen tons. For comparison, aluminum produces about 60 million tons per year. There are tons of cesium, but its role in global technology is disproportionately huge. That's why that quiet deal from 2019 wasn't just business, it was strategy. So, 70% of the world's cesium reserves are in one place, in the Canadian wilderness. But mining the stone is just the beginning. The real hell begins later, in the lab. Hypothetically, you need to sort millions of coins on a conveyor belt, all identical in appearance. They differ only in weight by 1/100th of a gram, and this must be done not by hand, but only chemically. Alkali metals are as similar to each other as identical twins, rubidium, potassium, sodium. In solution, they behave almost identically. The ions are similar in size and react similarly. Separating them is only possible by exploiting tiny differences in the solubility of the salts or by ion exchange. Previously, this was done by nitrate recrystallization, a tedious and time-consuming process. Now, solvent extraction is used. It's faster, but still messy and expensive. Once the cesium is finally separated as a salt, it still needs to be converted into pure metal. The cesium salt is heated together with calcium and barium in a vacuum furnace at temperatures above 1000 degrees Celsius. Calcium or barium removes oxygen, and the pure cesium evaporates, then condenses in a receiver. The entire setup is hermetically sealed because the slightest contact with air instantly oxidizes the product. The environmental aspect of the process is a separate headache. The solvents used to separate the alkali metals are toxic. The waste contains traces of heavy metals. It's hard to imagine that just a few decades ago, all this was simply dumped into the nearest river, and no one really cared what would happen next. Fish, water, people downstream. It was as if none of this had been considered. Companies are now required to submit environmental reports, build treatment systems, and account for every stage of production. This increases the cost of the metal, but at least rivers remain rivers. Are there alternatives? Scientists are looking. One promising area is bioleaching. Some bacteria can selectively accumulate certain metals from solution. Genetic engineering could theoretically create a strain that would specifically extract cesium from ore. The efficiency is low so far, but if successful, prices would fall and the process would become incomparably cleaner. In the Soviet Union, cesium was considered an extremely scarce strategic material. It was singled out as a separate item in 5-year plans. The shortage was so acute that companies sometimes switched to importing it. The main reserves were located in Siberia and Kazakhstan, but the geology there is more complex than in Canada, and the climate made extraction extremely expensive. Therefore, while Western countries were actively developing cesium-based atomic clocks and photoelectronics, Soviet industry was looking for ways to reduce its consumption. This was one of the factors slowing the development of Soviet precision electronics. All these difficulties of extraction. Why do you think so much trouble? What's so special about this metal, besides watches? Answer: electrons. Cesium has them uniquely. 1887 German physicist Heinrich Hertz noticed that if you illuminate a metal surface, electrons are ejected and elected. A year later, another German, Wilhelm Hallwachs, described the phenomenon in more detail. This is the photoelectric effect, the conversion of light into electric current. A beautiful idea, but practically useless until the right metal was found. The problem is that most metals hold on to their electrons too tightly. You need a very powerful light to knock any of them loose. This is impractical. Cesium has the lowest ionization potential of all stable elements. Let's translate this into human language. Imagine that cesium's electrons are sitting at the very edge of their orbit and are barely hanging on. The weakest push, the flash of a distant star, the beam of a flashlight in the fog or traffic lights, are enough at a distance of a kilometer, and an electron turning into an electric current. Cesium reacts to light in a way that no other stable metal does. This was first applied in cinema. Sound cinema, the kind you take for granted, required recording the soundtrack on film, which meant converting the light signal into an electrical signal. Without cesium photocells, early sound cinema systems were slower and required blindingly bright lighting. With cesium, it became possible to work in low light. But cinema was only a warm-up. The real application came with war. Mid-20th century. The United States of America and the Soviet Union competed in stealth warfare technologies. Whoever saw the enemy first at night would win. First-generation night vision worked on photomultiplier tubes. Weak light hit the cathode, knocking out electrons, which were accelerated by an electric field, striking a phosphorus screen, and a greenish image appeared on it from the darkness. The heart of the system was the cathode. It was made from a compound of 3 atoms, cesium, and a single atom of antimony. A thin film inside a glass tube. Without it, no night vision device worked. A sniper is blind at night. A helicopter can't observe. The Vietnam War demonstrated this with frightening clarity. American troops with night vision devices had a decisive advantage in night operations, but producing the tube required ultra-pure cesium. Any impurity reduced sensitivity significantly. While American engineers were working on the composition of the cathode, Soviet chemists were looking for ways to improve it. The arms race was not only for missiles, but also for atoms. And in parallel, another race, even more ambitious. Magnetohydrodynamics. It's better to break it down piece by piece. It will be clearer. Magnetic means a magnetic field. Hydra is a liquid or gas in motion. Dynamics, in fact, is motion. And now put it all together. If you pass a stream of hot conducting gas through a magnetic field, an electric current will arise in it. Just like that, directly, without turbines, without generators, without a single rotating part. Gas flows, electricity appears, almost like magic if you don't know physics. A conventional power plant works through a chain of transformations. We burn fuel, heat, water, the steam, turns the turbine turns the generator. Each link loses energy. Friction, vibration, heating. The efficiency of the best thermal power plants of the mid-20th century was 35%. More than half of the fuel's energy went up the chimney. Magnetohydrodynamics theoretically promised 40–50%. Silence. No moving parts. Sounds like a dream. And that's exactly how it was treated. But for gas to become a conductor, it needs to be heated to several thousand degrees. That's not enough. You also need free electrons. Here again, cesium. A few grams of cesium atoms per cubic meter of plasma dramatically increased its conductivity. Cesium became a seed, in English, seed, seeding the plasma with electrons necessary for current. In the 60s and 70s, the Soviet Union operated the U-25 facility near Moscow. It was a 25-megawatt MHD generator, the largest in the world. The Americans were pursuing their own programs. Enormous sums were invested. A power plant without rotating parts, or a military ship powered by a straight-through gas flow. Why don't we live in a world of MHD power plants today? Cesium proved to be too aggressive a guest. It corroded the ceramics of combustion chambers and penetrated metal filters. Recovering it cost more than the savings. The technology is beautiful, but indomitable. However, some things survived. MHD principles migrated to heat recovery systems in rocket engines, and the idea of alkaline seeds led scientists to a completely different place: space. Ion engines, the heart of deep space. Okay, you might say, the power plants didn't work out, but cesium still flew, just not as planned. Chemical fuel, hydrogen, oxygen, kerosene, are good for a powerful thrust. Putting a rocket into orbit and accelerating the craft is one thing, but a long journey to Jupiter or Saturn is something entirely different. An engine that uses a minimum of matter but runs for months without stopping. An ion engine does just that, charging atoms with an electric field and ejecting them at incredible speed. The thrust is weak, like a breeze, but continuous. Over months of operation, the craft accelerates to speeds that chemical engines can only dream of. And the first working fluid chosen for ion engines was, guess what? Cesium. Its lowest ionization potential makes it the easiest to charge. In 1964, the United States Aeronautics and Space Administration launched a spacecraft called Space Electric Propulsion Test 1. One of the engines used cesium. In 1970, a second spacecraft in the same program confirmed its performance in long-term mode. Later, cesium was abandoned. Xenon proved more convenient. The noble gas leaves no residue. It's easier to handle. But the first steps towards a flight into the depths of the solar system are made by this soft golden metal. And now, to a place you definitely didn't expect. 2 white coats. X-ray equipment uses image intensifiers. The principle is the same as in night vision. Photo multiplier. A weak signal from an X-ray hits the cathode, knocks out electrons, which are accelerated and produce an intensified image. Why? So that the doctor can see details with a minimal dose of radiation to the patient. The more sensitive the system, the less X-ray radiation is needed, the healthier the patient. Cesium in medical technology works as a protector. A paradox. It helps reduce the harm from radiation, while its radioactive twin, which we'll talk about later, does exactly the opposite. There is another direction that is on everyone's lips now. Quantum computers. Some quantum processor architectures use ion trap. A single atom is held in a vacuum by electric fields and irradiated with a laser. This atom becomes a qubit, a unit of quantum memory capable of storing information in a superposition state. Cesium is well suited for such traps. It has precisely isolated energy levels that can be controlled with lasers with high precision. It behaves predictably. Scientists at the National Institute of Standards and Technology in the United States and in European laboratories are experimenting with alkaline metal ions, including cesium, to build reliable quantum systems. If this seems like a distant future, the world's largest tech companies are already investing billions in this field right now. Another prospect that is not yet widely covered deserves mention: solar energy. Standard silicon panels have a physical limit to their efficiency. They capture only a certain part of the sunlight spectrum. Thin layers of alkali metals on the surface of the element can change the absorption spectrum, making the panel more voracious for photons. This is the so-called thermal enhancement effect. While these are laboratory prototypes, for now the principle has been proven. Night vision, MAG generators, ion thrusters, X-ray amplifiers, quantum computers, solar panels, cinema. And all this is one metal, soft, fluid, explosive, but it has a dark side. Almost like the title of a Pink Floyd album. And this side is much more frightening than an explosion in water. It turns out that cesium has a twin, not a chemical relative, but its own radioactive isotope. Stable cesium-133, the same one that measures time, is safe. But when the nucleus of uranium-235 or plutonium-239 splits in a nuclear reactor, cesium-137 is born among the fission fragments, radioactive. It emits gamma radiation. The half-life is 30 years. 30 years is the lifespan of a generation. If an accident occurred today, in 30 years, half of the cesium-137 would still be active. In another 30 years, a quarter, the contamination doesn't go away. It lives for decades, poisoning the soil, water, and plants. In April 1986, the Chernobyl nuclear power plant accident released about 85 petabecquerels of cesium-137 into the atmosphere. A petabecquerel is a unit of radioactivity equal to 150 decays per second. 85 of these units scattered across a vast area of Europe. A little more than one half-life has now passed. Cesium-137 decays into stable barium-137. About half has already become barium, but the other half is still active. Trees in the red forest near the reactor still contain elevated background levels. The soil in some areas is unsuitable for farming. The accident at the Fukushima Daiichi nuclear power plant in Japan in 2011 added to the problem. And here's what makes cesium-137 especially insidious. It is chemically similar to potassium. And potassium is vital for your heart and muscles. Body cannot distinguish cesium from potassium. Once ingested with food, with water, when exposed to air, radioactive cesium spreads throughout the body. Muscles, liver, and kidneys are irradiated from the inside, slowly, silently, and continuously. The most famous incident, not involving a reactor or a bomb, occurred in 1987 in the Brazilian city of Goiânia on the Fool's Gold Canal. We've already briefly mentioned this incident. An old radiation therapy unit abandoned by a private clinic ended up in a landfill. People opened the casing and discovered a substance with a bluish glow inside. They didn't know what it was. 4 people died. Hundreds received significant doses of radiation. The land for several blocks had to be bulldozed and packed into concrete containers. One of the most serious radiation incidents in history. No reactor, no bomb, no war, no war. Just an abandoned device and ignorance. The main lesson of Goiânia is simple. Cesium-137 is dangerous not when it is known, but when it is not known. That's it. A sad pun. And here's another interesting fact. Cesium is present in your body. On average, an adult's body contains 20 to 30 micrograms. It enters the body through food, soil, plants, and animal meat. The body accepts it as a potassium analog and partially absorbs it. The biological half-life is about 70 days. Then it is excreted. If it's stable cesium-133, it's no big deal. The concentration is negligible. But if there are traces of cesium-137 in the environment, it is absorbed in the same way. There's the same chemical door, only behind it is internal radiation. In the areas around Chernobyl, studies have shown that people who remained in moderately contaminated zones had cesium-137 concentrations in their bodies that were tens and hundreds of times higher. Radiation works statistically. At the population level, disease rates increase. At the individual level, it's a risk, not a death sentence. That's why dosimeters in risk zones aren't bureaucracy, because what you can't see or feel can be working inside you directly. Now, people who work with cesium professionally know this better than anyone. Engineers, chemists, reactor operators. Their work requires special concentration. Cesium causes severe chemical burns to the skin upon contact, but something else is even more dangerous. Cesium oxide pores, which form during combustion. Inhalation leads to lung damage and edema. Safety regulations are strict. Special suits, breathing masks, working in boxes with a nitrogen atmosphere. Violating the rules is punishable because the price of error is too high. In the history of the industry, there are cases where inexperienced people tried to test the reaction of cesium with water without proper preparation. The results were tragic. The element that controls time can take it away from you instantly. Now to a place you definitely didn't expect, to the bottom of the North Sea. An oil platform. Storm. Under your feet, a well 6 kilometers deep. Down there, the temperature is several hundred degrees, and the pressure is capable of flattening a steel pipe. The drilling crew is pumping a special solution into the well. It must be dense, so that the pressure doesn't collapse the rock walls, heat resistant, so that it doesn't decompose in the hell below, chemically inert, so as not to damage the oil-bearing formation. Ordinary water is no good. Standard weighting agents, borate, calcium chloride, work up to a certain depth. At 6 kilometers, they no longer work. That's where cesium formate, a salt of cesium and formic acid, comes in. A transparent liquid with a density of up to 2.2 grams per cubic meter of water. It's almost twice as heavy as water. Non-toxic, doesn't corrode rock, and is easily extracted and reused. Recycling efficiency is up to 95%. One of the most expensive drilling fluids in the world. But the loss of an ultra-deep well due to a collapse costs hundreds of millions of dollars. Cesium formate circulates in a closed cycle between platforms in the North Sea and the Gulf of Mexico. The metal, once obtained from tens of tons of German mineral water, now supports deep-sea oil production. But the oil platforms weren't the strangest place where cesium came in handy. In the 1980s, it found itself next to a much more nerve-wracking topic: space defense. 1983, President Reagan announces the Soyuz Strategic Defense Initiative, IKEL, popularly known as Star Wars. The goal: to intercept Soviet intercontinental missiles in space. Orbital lasers, kinetic interceptors, beam weapons. Beam weapons. A beam weapon is a directed stream of accelerated particles. One of the projects involved a beam of neutral hydrogen atoms. To synchronize the entire interceptor system in real time, a new generation of clocks was needed, more accurate than anything that existed. Cesium atomic clocks were considered because coordinating such a system required an accuracy unattainable by any other technology. The program was never implemented, but some of the developments and design principles for miniature atomic clocks migrated to the civilian sector. Today, there are atomic clocks the size of a coffee mug, and some are no larger than a microchip. They consume less than 100 milliwatts and operate on batteries. Accuracy of 1 second every 300 years. They're already in military drones, emergency beacons, and underwater navigation systems. A smartphone with such hardware could determine its position without a satellite, using only its internal clock and motion sensors. This is called dead reckoning navigation. The military is already using this technology in case an enemy jams the global positioning system signal. Cesium in your pocket. A backup compass at the atomic level. Another interesting thing: every operating reactor in the world accumulates cesium-137 in spent fuel. It's stored in pools of water. The water cools the rods and absorbs neutrons, but this can't go on forever. Permanent storage facilities are needed. Finland is building one now. Onkala is an underground labyrinth in granite at a depth of 400 meters on the Baltic coast. Containers with spent fuel will be lowered there, sealed, and gone forever. The goal is to isolate the material 100,000 years. Think about it. 100,000 years ago, anatomically modern humans hadn't yet emerged from Africa. We're trying to build a vault that will last longer than our civilization. And that's what makes the task truly strange. The main question isn't engineering, it's linguistic. How do we warn people of the future about the danger? In 100,000 years, our languages, symbols, and signs may become incomprehensible. This is called the nuclear semiotic warning problem. Philosophers and linguists are racking their brains. What should we paint on the wall of the vault so that a person 100 centuries from now understands? Stay out? One suggestion, an image of a man writhing in pain. No words, no symbols of danger. The universal grimace of suffering. An image that anyone in any era will understand correctly. We're creating a language for a civilization that doesn't yet exist, for the sake of a container of cesium. Foreign dessert is a favorite topic for many. Where did cesium come from anyway? Not in Canada, not in Namibia. Where did it come from in the universe anyway? Well, supernovae, of course, the eternal heroes of our videos. Yes, we often return to them, because the history of the elements simply cannot be avoided. If you've been watching our videos for a while, you already know this diagram in general terms. But if this is your first time, here's a quick summary. When a giant star dies, it explodes. Inside this explosion, the temperature is millions of degrees, the pressure is monstrous, and heavy elements are born there. Neutrons smash into the nuclei, creating more and more new isotopes. Cesium is formed in two ways: by slow neutron capture, the so-called S process, and by fast neutron capture, the R process. When a star explodes, the debris is scattered across space. After millions of years, part of this cloud condenses into a new planet. Part becomes a rock at the bottom of a lake in Canada. Part becomes an atom in your watch. Part is in your body right now. You carry the ashes of a dead star within you. This is not a metaphor. It's geochemistry. Our galaxy is low in cesium. Its concentration decreases with distance from the center. Our solar system formed in a relatively rich zone. If Earth were farther from the galactic center, there might be less cesium. Atomic clocks as we know them wouldn't exist, i.e. east. Navigation would be worse. The internet would work differently. All of civilization could have taken a different path because of the distribution of one element in the interstellar cloud from which we emerged. Everything hangs in balance, and this balance was formed long before us. And here's the question I promised to return to at the beginning. So why do we need such precision? Why a second accurate to the nanosecond? Why a clock that's error-free for 300 million years if the human lifespan is 100 million at most? Example. Right now, a global positioning system satellite is hovering at an altitude of about 20,000 kilometers. The signal from it to your phone takes about 70 milliseconds. The navigator receives signals from 4 satellites simultaneously, subtracts the difference in delays, and determines your location. The accuracy is 10 meters, sometimes less. Now imagine that the clock on the satellite is off by 1 millisecond per second. Just one. Light travels 300 kilometers in a millisecond. The navigator will show you at 300 kilometers off your actual location. The plane will miss the runway. The container ship will run aground. That's what precision is for. It's woven into the world around us. We don't notice it until it disappears. But there's something else that's rarely talked about. Cesium atomic clocks are so accurate that they've revealed something inconvenient. Time passes at different rates depending on where you are. This is Einstein's general theory of relativity, confirmed experimentally. Clocks near the Earth's surface tick slightly slower than clocks in orbit. Gravity slows time. The difference is about 38 microseconds per day. Seems trivial. Now, without adjusting for this effect, the global positioning system will start to err by 10 kilometers per day. That's why a relativistic correction is built into the software of every satellite. Every time you look at your GPS, the program makes a correction for Einstein's theory automatically, invisibly. Einstein working in your pocket. Before 1967, this precision didn't exist. There was a second tied to the Earth. In 1956, the so-called ephemeris second was adopted, based on the calculated speed of the Earth's revolution around the Sun at a specific moment in history. A standard that was obsolete at the time of its adoption, because the Earth was already rotating differently. Cesium solved this radically. Let's not take the average speed of something that never changes at all. the atom. The solution turned out to be so good that it created the opposite problem. Our clocks have become more accurate than the planet on which we live. Coordinated universal time, which the entire world observes, is a compromise between the atomic second and the actual rotation of the Earth. A parallel system, UTC-1, monitors the planet's actual position. The two times diverge. The Earth slows, and the Moon's tidal friction slows it like a hand on a wheel. To ensure that coordinated universal time does not diverge from solar time by more than 0.9 seconds, international organizations periodically add a leap second. Every few years, instead of 86,400 seconds per day, there are suddenly 86,401. The last time was December 31, 2016. Programmers will at this moment. For a computer, 61 seconds in a minute is a logical error. Servers freeze. Stock exchanges suspend trading. 1 second, and systems written without taking this nuance into account crash with an error. In 2022, the International Bureau of Weights and Measures voted to abolish leap seconds by 2035. Atomic time will win definitively. Coordinated universal time will diverge from the Earth's rotation, and for the time being, that will be fine. When the divergence accumulates to a minute, around the end of this century, we'll have to think about it. We chose cesium. Now the Earth is adapting to the atom, and in parallel another race is underway to replace the standard itself, optical atomic clocks. The next step after cesium. They operate not on microwave radiation, but on visible light or near ultraviolet. The frequency of optical radiation is 100,000 times higher than microwave radiation, meaning the accuracy is 100,000 times higher. Prototypes are already operating at the National Institute of Standards and Technology in the United States, the German Physikalische Technische Bundesanstalt, and the Japanese National Institute of Advanced Industrial Science and Technology. They use atoms of strontium and terbium, aluminum. It seems the end of the cesium era. Not quite. The International System of Units defines the second in terms of cesium, officially and legally. All other clocks are calibrated against it. Changing the definition itself would require a decision by an international conference. The transition is expected around 2030, but cesium clocks will be around for decades to come. They're cheaper, more compact, and more reliable. They can be made the size of a coffee mug, while optical clocks currently occupy an entire lab. Now comes the moment I've been building the story for from the very beginning, when all the threads converge. Cast your mind back to September 2019. A quiet deal. A Chinese company is buying control of 70% of the world's reserves of a metal without which no satellite navigation system on the planet functions, without which the internet can't be synchronized, without which super deep wells can't be drilled, without which quantum computers can't be built, without which night vision and autonomous navigation for military drones are impossible. The country that controls the main source of this metal is simultaneously building its own Beidou satellite navigation system, developing quantum technologies, expanding nuclear power, and expanding its space program. 1 kilogram of high-frequency cesium metal costs between $70,000 and $100,000, 30 to 50 times more than gold. There is no public exchange, no futures. The market operates on closed contracts between several players. It is opaque and vulnerable. The European Union has included cesium in its list of critical raw materials. The United States is seeking alternative sources in Australia, Brazil, and Namibia. So far, nothing comparable has been found. How long will the reserves last? Geologists estimate a couple of centuries at current consumption, but demand is growing. Quantum computers, new types of engines, and expanding space programs, perhaps we will face a cesium crisis sooner than expected. Either they will find a replacement, or they will learn to effectively recycle old devices, or bioleaching will finally leave the laboratory. History knows of examples. Gold became scarce for coins. They switched to banknotes. Oil is undergoing a transformation right now. Cesium may follow suit. When Europe realized its dependence on a single gas supplier, it became a front-page crisis. Cesium is quieter. The market is small, non-public, and incomprehensible to most. But the metal is critical, and the dependence is real. And here's the strangest paradox of this whole story. We can measure time better than anything else in the universe with an accuracy of 1 part. In an accuracy of 1 part in a number followed by 15 zeros. But the question of what time is remains open. In general relativity, time is one of the 4 dimensions of space-time. It is curved by mass, moving faster away from heavy objects and slower nearby. We measure it. We use it. In quantum mechanics, time is a parameter, not an observable quantity. It is not quantized. It flows continuously, unlike energy, which arrives in chunks. Why? No one knows. This is one of the open problems of theoretical physics. We measure time with unimaginable precision, and yet don't understand what we're measuring. Cesium stands at the foundation of this paradox. He is the standard for something whose nature we don't understand. Roger Bunsen lived to be 88 and died in 1899, just as the first automobiles were just appearing on the streets. He didn't live to see airplanes, radio, the atomic age, the internet, or satellites. In 1860, he sat in a laboratory in Heidelberg, blue line in a spectra, staring at the blue line in a spectroscope and asking what it was. He didn't know he was starting a bud, the end of which is still invisible. Redefining the second. Clocks more accurate than celestial mechanics. Oil wells 6 kilometers deep. The first ion engines. Night vision. Quantum computing. Underground storage in Finland designed to last 100,000 years. A quiet geopolitical deal in 2019. Einstein in your pocket. The blue line in a spectroscope in 1860. In your GPS in 2025. A straight line, without breaks. We live in the first era in history when humanity measures time more accurately than the motion of celestial bodies. For 200,000 years of our species' existence, we looked at the sun, the moon, the stars. Wikisigi. They told us what time is it. Now we look at the atom. This didn't happen according to plan. It happened because a chain of curious people asked questions that had no practical answer and received answers that changed everything. Bunsen wanted to understand why flames glow blue. Rotby wanted to understand whether atomic vibrations could be used as a clock. Essen wanted to build that clock. None of them thought on doing this so that in 60 years people will look at their phones and know their coordinates with an accuracy of 10 meters. That's how science works. Not a plan, but a chain. Cesium, element 55. Softer than wax, at the heart of the most precise instruments in history. Explodes from water, works in drilling fluids on the seabed. Rare in every satellite, in every navigator, in every deep drilling platform. Well, never seen in everyday life. And without it, this life would look completely different. A stable isotope, a keeper of time, a radioactive marker of disaster. 2 faces of the same name born in a supernova explosion found in German mineral water. Friends, thank you for watching to the end. If this story caught your attention, write your opinion in the comments. I always enjoy and find it interesting to read them, and I try to answer whenever possible. If you have questions, disagreements, or corrections, write. This helps our channel get better. Next element coming soon. He's not who they think he is either. See you on the Fool's Gold channel.